Let's go stand on the sun. I'm going to put our brick on the sun. So I'm going to leave that formula up. And we've gone over this. The universal symbol for the sun is a circle with a dot in it. Okay, and that's, nope, that's not on your sheet. But 6.67 by 10 to the 11, negative 11, times the mass of the sun. I'm being lazy with units here. I shouldn't. Sorry, kilogram. Mass of the sun is 1.99 by 10 to the 30. Mass of my brick is 10 kilograms as usual. We're going to divide all that by the radius of the sun squared. 6.96 by 10 to the 5. That's in kilometers. So that's going to be 10 to the 8 meters. And we're going to square that one. Someone want to punch all that into a calculator and tell me what it is? Because I don't know. I can't do that in my head.
The exponent for the 10 is 30.
Yes, good catch. Thank you.
I got 55.04.
Yeah, 3 significant figures is usually enough. Anyone else can confirm that? How does that compare to the weight of our brick on Earth?
It's a lot lighter.
It's lighter. Isn't that a little... Does that match, or... Does that meet or defy your expectations?
That means,
Why?
well, we know people from, astronauts going on the moon, that we know they were lighter, so it makes sense that if a brick goes up there, it'll be lighter as well.
Yeah,
Plus, it's also a smaller, the moon also has a smaller mass than the Earth does.
This isn't the moon, this is the sun.
Oh, you said sun, sorry.
Yeah. The sun is way more massive than the Earth.
Yeah.
The sun is 1 million times more massive than the Earth.
Then no, that doesn't make sense.
Yeah.
I got a different answer.
What'd you get?
2,740.06.
2,000.
740.062.
That's enough. There's 3 significant figures.
That's what I got too. Yeah.
So we get some more agreement on this. How do we square this circle? How do we convince ourselves? Okay. One thing we can do is called dimensional analysis or order of magnitude approximation. The sun, so forget about this number out here, only look at this number up here, compare it to the Earth. So the sun is 10 to the 30, the Earth is 10 to the 24, the difference between the two is 10 to the 6. So we expect, based on that difference, the weight alone. So if the sun was somehow compressed down to the size of the Earth, then we would expect our brick to weigh 1 million times more than it does on the Earth. But that's not the only story. So we have to take that into account as well. The size of the sun is enormous compared to the Earth. So the radius of the sun is 10 to the 3, 10 to it's about 100 times larger than the Earth in terms of radius. So 100 or so 10 to the 2 squared. When you take an exponent and raise it to another exponent, you multiply the two. So 10 to the 2 to the 2 is 10 to the 4. So we want something that's 10 to the 6 divided by 10 to the 4, which is 10 to the 2. So we want something about 100 times more massive than what it is on Earth. Did you follow all that, or should I write it all down?
So you're saying that like we should just, if we're like on one of these problems, we can just easily multiply it by 9.8, and then that's how we kind of like check our answer from the other places.
That's for the Earth. You
Right,
can
so
multiply it
9.8
by.
is the Earth, so then we can compare the 24 is our exponent to the other places.
Yeah.
So we check our work.
Can we figure the constant out for each body?
What's that?
Can we figure the constant for each body?
Are you talking about G?
Like how 9.8 is for Earth? Can we figure that out?
Oh, yes, you figure out surface gravity for every planet in the solar system and memorize it. Yeah, sure, and there's probably a table in the book that lists it, because it's an important piece of data for computer modeling of atmospheres, for instance. So, yeah, you can do that. But you know certain things, like you've seen videos of the astronauts on the moon. The moon has less gravity than the Earth, so you should expect a smaller weight on the moon. Yeah.
I found out what I was doing wrong, just in case anybody else has a TI-36 and is also doing this. I just realized this e to the power is not the same as 10 to the power. It's,
Oh, the lowercase e.
Yep, so that's what was thrown. That was.
Yeah, that's
explains
the.
why all my wrong math.
Yeah, e to the x. That's the natural constant.
Yeah.
It's like 2 point something, and then you raise it to some value. So yeah, your calculator, you want to use e. In some calculators, it's e, and that is by 10 to the whatever. It follows. Here you punch it. Okay, broader point. When it comes to solving problems in astronomy, you're dealing with numbers that you're not used to dealing with, because, yeah, look at these numbers, they're freaking huge. So let your intuition guide you. Let your intuition kind of set the goalposts for your field goal kick. So, for example, the Earth, we know weights are about 10 times more than their mass. Like I mentioned, up on the moon, we expect it to be less than that. And we went through the trick of how we can do that for the sun to figure out about how much more it's going to be. And then that gives you some more confidence that this is the right answer rather than that. So we'll erase that guy.